Good morning. So today we thank the Almighty God for giving us life. We ask that wherever we study, you give us the mindset, the brain to understand, so that on day of account, we will be able to deliver through Christ our Lord. Amen. So today we'll be looking at muscle physiology. Muscle physiology. Initially, we looked at the bones, and then we also look at the bone physiology, looking at the development of the bone, either by intramembranous or endochondrial ossification. And then we also look at the bone healing processes and all those things. These things we actually saw in both anatomy and physiology. So today we want to look at the other aspect of the musculoskeletal system, which is the muscles. So we want to look at how muscles perform their function, and what characteristics these muscles have to perform their function. So at the end of the lecture, we expect that we will be able to know the characteristics of muscles, explain how these characteristics leads to their function, and then the histological makeup that bring about the functions of muscle. So muscles allow for body movement, as we know already from the beginning of musculoskeletal introduction. Maintenance of posture, they are built on the bones. They allow for respiration. Okay, when the respiratory system, you have the respiratory muscles contracting and relaxing. They allow for increase in the thoracic volume or decrease in the thoracic volume or the pleural volumes, which will lead to the inhalation and exhalation of air. Muscles also will allow for the generation of heat that keeps the body warm. And as I am speaking to you, it is the muscles that are contracting and then relaxing that is allowing me to talk. And then with the function, with the association of the vocal cords as attached, you can hear the sounds and everything that is happening. So whatever you do is muscles. You look at a beautiful lady around you, it is muscles that are rotating your eyeballs to see that beautiful lady. So everything is muscles. You are sitting down, you see a beautiful lady and your penis is erected. It is muscles. So all these things that we are coming to talk about. And then muscles will also allow for constrictions of organs and vessels, especially when there is vasodilation and vasoconstriction. Then the heart also beats. That is also muscles. Let's look at the properties of muscles. So muscles are usually having four main properties: contractility, which ability of the muscle to shorten with force; excitability, the capacity of the muscles to respond to stimuli. I give you a slap, and then you try to you also try to respond. That is what you feel, the pain and all those things. That is excitability. Extensibility, as the muscle can be stretched to its normal resting length or beyond its limit degree. But when you stretch the muscle too much, so that it goes beyond its extensible limiting degree, then you are going to associate the muscle to what we call muscle tear or pull. Muscle tear. Now, elasticity is the ability of the muscle to recoil to its resting length after it has been stretched. We have three main types of muscle. We have the skeletal muscle, the smooth muscle, and the cardiac muscle. The skeletal muscles, by the name, it is attached to bones, and histologically, these muscles are striated. They are voluntary. That is why you can say, I'll slap you, and then your hands are up. They can also be involuntary due to reflex activities. They are multinucleated, and the nucleus is also located peripherally. But when we take the smooth muscles, which make up the organs within the body, they are made up of walls of hollow organs, and then they are uninucleated. They are non-striated. I'll explain what this striation means later. They are involuntary and they have gap junctions between them. Cardiac muscle is also another muscle that makes up the heart and the most proximal part of the large vesicles, such as the aorta and the vena cava, and then the pulmonary trunk. They are also uninucleated, they are striated, involuntary, and then these are made up of what? The cells are joined to each other by the intercalated disc. So this is to show you how the skeletal muscles are. You can see the skeletal muscle with the peripheral located nucleus. These dark and light bands that you are seeing, this arrangement of, you can see some places are dark, some places are light. When I say dark, it doesn't mean black. I mean, if it is pink, more pink, light pink, more pink, light pink. That arrangement that we see there, as we can see here, is what we call the striations. Now, one thing we have to do is that from myogenesis, muscles will actually develop from the muscle myoblasts, which are vessels that make up cells that make up the muscles. Okay, and then they actually are found within. They also have some form of connective tissue that hold the muscles together. And then within the connective tissue, we also have some blood and nerve tissues that are associated with muscles. So when we look at the organization of a muscle, this is a whole muscle organ. Okay, for instance, you take the biceps brachii. The biceps brachii is an organ. Now, this organ has smaller muscle units, which is called the fascicles. So the fascicles are inside here that we can see. The fascicles, which are enclosed by a connective tissue known as the epimysium. Now, these fascicles are also made of smaller units, which are known as what? Muscle fiber. These are the fiber. And so this fiber also, a lot of fibers which make up the fascicle are also enclosed by them. Perimysium, and then each muscle fiber is also enclosed by what? The endomysium. Now, let us continue to look at the components of the endomysium. So when we cut this at this section, this is what you are seeing. That's the perimysium, and then this is the endomysium with that. Now, when we take the endomysium, then we are now having the myofibril. These are myofibrils. This is a myofibril, this is a myofibril, this is a myofibril, this is a myofibril. So the myofibrils are actually enclosed by the membrane of, so this is a cell, this is a muscle cell, membrane of the muscle cell, which we call the sarcolemma. Okay, the sarcolemma. So the sarcolemma has a satellite cell attached to it, which is enclosed overall by you can see that now, you can see the nucleus, but initially you are not seeing any nucleus. So this tells you that this is the muscle cell. So when you look at the gross presentation of the muscle now, you can see that we have some blood vessels running through the connective tissues. That's the epimysium, perimysium, and the endomysium. And then you can see that nerves are also kind of attaching to, the yellow ones are attaching to the muscle fiber around the sarcolemma. And this is going to form what we call the neuromuscular junction. The neuromuscular junction. Now, the muscle is also enclosed in one connective tissue we call fascia. The fascia encloses the whole epimysium. So the epimysium in certain cases are also known as the fascia of what? Of the muscle organ. So for embryologically, we say the myoblast will become will develop convert itself to some forms of muscle fiber developed through the fusion of mesodermal cells called myoblasts. So these myoblasts are mesodermal in origin. So they grow into the myocytes, and then eventually we are having the immature muscle fiber. This immature muscle fiber continues to grow, and then we are having this. So this is an example of the development of the skeletal muscles, the skeletal muscles. So this is just to show us the organization that we were talking about earlier. So looking at the internal organization for the myofibril now. So we take a myofibril. The myofibril is made up of the thick filament, which we call the myosin filament, and then the thin filament, which we call the actin filament. Now, it is this actin filament and the thin filaments, their movement that brings about the gross anatomical movement of the muscles. So the contraction and the relaxation of the muscle, that is the muscle shortening and becoming longer, comes from this side of the muscle. And because of these dark and light bands, here what is dark and here that is light, we term this side as what? These are the striations. So this is what give around all these things that we are seeing here, the striations we see in the whole muscle. So as we can see, the muscle is enclosed by the sarcolemma. So everything that we have here is the sarcoplasm. That is the cytoplasm of the muscle. That's the sarcoplasm. And then under the sarcoplasm, we have some mitochondria that is supposed to energize when it comes to respiratory activities for ATP production. We can also see the sarcoplasmic reticulum, and then the triad, which is made up of what? We can talk about the tubules, okay, transverse tubules, okay, the transverse tubules, the terminal cisternae, they are going to continue to make up the triad. So eventually, to see the striations better, so these are the thick filaments, which are kind of having thin filament intertwined with them. The smaller thin red lines are known as the thin filament. So where the red lines meet, you see that it is forming some Z disc, Z shape. So we call this as the Z line or the Z disc. So the distance from one Z disc to another Z disc is known as the sarcomere. That is the contractile unit of a muscle. So you can see that here, the length of the myosin is making up the A band. The A band. The length of the myosin is making up the A band. While the length of the actin, where you do not have the myosin, the thick filament overlapping, is called the I band. So the I band, in the middle of the I band, you see the Z disc. Now, also where we do not see the overlapping of the actin filament over the myosin is what we call the H zone of the thick filament. So we can see the thick filament, and then the titans are the ones that connect the end of the thick filament to the Z discs. All this to ensure that the stability of the muscle is thin. So this is what we'll see when it comes to electronic microscopy. So eventually, we can now see it better here. So this is the A band. So from here all the way to here will be the M zone. At the midpoint of the M zone, that's the M line. And this is the limit of the contract. You cannot contract your muscle beyond a particular limit. So that is what we call the contractility limit, the contractility limit. And then we can also see that the titans are where the ends of the muscles are connected, the myosin filaments are connected to the Z discs of the actin filament. So when you take a cross section through the muscles, you see the Z lines in this form. The I bands will be like this. The titans will be the green. The M lines will be very thick because they are thin. The H zone should be like this, and the zone of overlap will be like that. And this is what we usually see. So for muscles to contract, what happens is that we have a sliding mechanism, okay? The going back shortly, a sliding mechanism. The myosin have heads, which we call the myosin heads. So the actin filament will will slide over the myosin head. So when they slide, as if they are resting, then they move in this direction. So the H zone becomes bigger. But when they are contracting, then they slide inwards, and then the H zone becomes smaller. And then you have the muscle becoming shortened. One thing you have to note that during the contraction of the muscle, the myosin and actin lengths do not change. It is the movement of the myosin in the actin, the actin into the myosin that cause the shortening, okay? So the shortening is only seen usually from the sarcomere length. So this is, for instance, you can see this is the H zone now, okay? The whole of the length here is I band. So look at the M line. This is the M line, and you can see where the actin filaments are ending. When the muscle is at rest, this is how it is. But when it is contracting and it's doing the sliding movement, now you can see where they are, okay? So the lengths are the same, but just that the distance shortens. So this is just to show you an overall application of the muscle. And see how it is contracting and eventually contracts. Now, physiologically and more histologically, you can see this is the myosin heads I'm talking about. These myosin heads will form a cross bridge with the actin filament. And then eventually what happens is that the triad comes in, which is the tropomyosin, troponin, and the G molecules. So the G molecules are actually seen within. So the actin filament is made up of the G molecules, the tropomyosin, and then the troponin. The G molecules, tropomyosin, and then the troponin. And then we then have the two heavy chain. The myosin is made up of two heavy chain, and then we also have the heads, and then we can also see the light chain regions, and then the hinge region. So this is just to show us how the myosin filaments look like. So for the myosin filaments, what we can see, as we are speaking about, the lighter chains, the hinge region, and then the heavy chain. So this is just to tell us that the size is 20 kilodactyls, 25 kilodactyls, and all those things. So that is for the thin filament. Looking at the thick filament, this is what you see at electronic structure. So eventually, the M line that we see in this format, the M line is made up of the myosin filaments. Within the myosin filament, and then these are connected to each other by the cross linkage. We have the M1 cross linkage, the M4 cross linkage, and then the M3 cross linkage. So if I ask you to give the physiological description or formation, this is what I expect you to tell me. And then we've already seen the compositions of the thin filament. So now let us look at how cross bridges are formed and how muscle contracts physiologically. So this is what you have, okay? So eventually when a signal lands, let's say a nerve gives a signal to the muscle and then there is depolarization in the membrane. So what happens is that first, you can see that here the actin filament and the myosin filament do not, the head, they are not in contact with each other. You can see, okay, myosin head are not in contact with the actin filament. So the muscle actually is resting at this stage. Now, so in the resting sarcomere, we have ADP plus P eventually. So when a signal comes in, and then, so when calcium influx the cell, then what is going to happen is that there is going to be phosphorylation of the muscle, that is usage of energy. And then this is going to cause the movement of, you can now see how the hinges are moving very long to attach the myosin heads to the troponin substance of the actin filament. Now, as they connect, it will cause, you can see how this will move. So it will cause the gliding movement of this one over this, and that is what is going to cause the muscle to move inwards. This one to move inwards, this one to move inward. So this is where the cross bridges are formed. So step 3 is when there is pivoting of the muscle. It is rotating, and then it is causing this one to move, Then eventually, so at cross bridge, so when this happens and it is the signal is fast and the action is taking place, it has taken place, then we have the cross bridge detachment. So here there is what? Phosphorylation of ADP to form ATP, and then you go back to the resting stage as how it was. So this is just to show what I was talking about. We rotate and then bind to the troponin substance of the actin filament. And you can see this one coming in. These ones are the calcium together. These are the calcium, and you can see the ATP doing all their activities over there. So the ATP bind, which is the green one, you can see. So this is ATP. Before it attaches it to phosphorylate, so you see that it breaks off, and then you have ADP. Then you have when calcium comes in and there's a signal before the whole thing starts. So calcium will bind to the what? The troponin substance, and before the whole signal thing takes place. So eventually what I was saying is that first, there is actually so what you see here is that there is a repolarization state, or a polarized muscle. You can see the positives at top, negatives inside. So this is a polarized muscle. So what is happening is that when you have a signal from the nervous system, which gives the signal, what happens is that we are going to cause you are having a resting membrane potential. So at resting membrane potential, you don't expect the muscles to this. So they are just what? Polarized. So the membrane voltage difference across the membrane is what we call the polarized state. Now inside the cell, we have more potassium and chlorine as compared to outside the cell, where we have what? Sodium and at times calcium, especially when it comes to the heart muscle, calcium. So this must exist for action potential to take place. So eventually you have, this is the neuron, and then this is the muscle. So what happens is that we want to see how the action takes place at the neuromuscular junction. So what happens is that when we look at nervous physiology, we'll be talking about something we call the preganglionic and postganglionic nuclei, or we are looking at the end synaptic joints and then their activities. So what happens is that at the end of, let's say, at the end of the muscle, we have one neurotransmitter we call the acetylcholine, which is going to be released for signal transduction. So this is also happens when there is a calcium influx into the nerves. So when there's calcium influx, this is going to cause action potential in the muscles. Now, when this happens, it is going to cause acetylcholine binding to the receptor, cholinergic receptors. And when this there is a binding, there's a conformational change which causes these gating substances to open. I explained gating mechanisms within the earlier lecture. So you can now see that there is influx of sodium into the muscle membrane or muscle, and then there is what efflux of what potassium. So this mechanism that is happening at the synaptic cleft, the synaptic cleft is going to cause a transduction of what signal in the membrane, and this is going to lead to what the activation of what we saw earlier for the actin filament, for the myosin filament to connect to bring about the information. So during depolarization, there's a change in the difference across the plasma membrane, making the charge inside of the cell less negative and the outside of the place less positive. But during repolarization state, the depolarization phase, the membrane potential changes from approximately negative 85 millivolts to approximately positive 20 millivolts. So during the resting phase of the resting membrane potential, the inside of the plasma membrane and the outside, the outside of the plasma membrane always goes back to the threshold. Let me say, it goes back to the polarity in which they were first. So when you cross this polarity, come down a bit. So this is the depolarization phase. Now this is the depolarization mechanism. Then the phase comes, and then the muscle will repolarize and then goes back to its resting stage. So what happens is that action potential come in phases, and it can also come as an all or none principle, like when camera flash system, every light beam comes out at again. Can also come in propagating mechanisms where it's pressed from one location to the other location. But usually what we see in the skeletal muscles are the phases of depolarization and repolarization membrane. And the frequency of action potential is the amount of action potential produced per unit of time. So next thing we are talking about here is excitation, contraction, coupling mechanisms. So what happened is that this is a mechanism where action potential causes muscle fiber to contract, and it involves the sarcolemma, transverse tubules, terminal system like sarcoplasmic reticulum, calcium, and troponin. We have already explained this. So let's look at muscle twitch. Muscle twitch. When we say muscle twitch, muscle contraction in response to a stimulus that can cause an acting potential in one or more muscle fibers. And the muscle twitch comes in phases: the lag phase, that is the latent phase, the contraction, and the relaxation phase. So at the lag phase, what happens is that a stimulus is applied, then you begin to have the mechanisms coming in where you have action potential across the presynaptic cleft landing on the receptors. Then we are going to have depolarization and all those things coming in, and then the contraction happens. Then when the contraction reaches its extremum point, then the relaxation phase also comes in. So this is just to kind of project the lag phase, contraction, and then relaxation phase all together. So all these things tell the strength of the muscle. So eventually, when your muscle is smaller, you may not see this. Someone who has a very bigger muscle, you will see this more conspicuously per time, okay, per time. So at times these things become a bit bigger. The curve over here, the plateau over here, you see it a bit bigger. So this is just to show the stimulus strength and muscle construction. So for the all or none law for the muscle contraction, what happens is that the contraction of the equal force in response to each action potential. So you realize that all the muscle will try to respond to each of the action potential. So within this, we have sub-threshold stimulus. There's a threshold stimulus, and then there's a stronger than threshold stimulus. So this will tell the stimulus strength, and then the strength of the stimulus also is directly proportional to the muscle contraction abilities. Now, there is something we call the motor units. Now, motor units are when a single neuron innervates muscle fibers, or it's the innervation of muscle fibers by a single motor neuron. That is what we call the motor unit. So it is a motor unit that leads to what? The depolarization, where you have the information all coming in to bring about all that we need to know. Now, so we'll quickly look at types of muscle contraction. We have isometric muscle contraction when there is no change in length, but tension increases within the muscles. So usually you see this in the postural muscles of the body. Okay, like the muscles that you don't, like you sit down, your back muscles and all those things. Then we have the isotonic, where there's change in length, but tension constant. That is isotonic. And the isotonic can be concentric or eccentric. When it is concentric, it means that it overcomes an opposing resistance and muscle shortage. When it is eccentric, the tension maintained, but the muscle lengthens. So for concentric muscle contraction, the contraction is such that it overcome an opposing resistance. For instance, I want to push something. I want to push a car. I'll be applying more of what? Concentric activities. And then for eccentric, you have the tension remain. Muscle tone. So we are seeing isometric contraction, isotonic, and then muscle tone. Yeah, constant tension by muscles for long period of time. That is what we call muscle tone. And usually at times you see these things within spasms. So for here, we are looking at the ability of the muscle to contain a tension for over a long period of time. So this is what we were talking about when we were looking at the all or none law for muscle fibers. So we are looking at the sub-threshold limit, no motor unit response. Threshold stimulus, 1 motor unit response. Then maximal stimuli, increasing number of motor unit response. Maximal stimulus, all motor unit response. Supramaximal, that means all motor units also response again. So you see that almost this and this are the same. So when it reaches, it means that the muscle cannot go beyond that, and it has to move back to its original application. So what happens is that the subunit response, which just starts at the myofibril level, gets to threshold stimulus response, which gets to the fascicular level, and then we are getting to, sorry, the fascicular level at the subaxial, and then eventually we are having the whole muscle contracting. So a whole muscle contract with a small or large force, depending on the number of motor units stimulate units that stimulate the muscle to contract. Now, for you to know the total force applied to the the muscle, you need to know the end product of the multiple wave. So we call something multiple wave summation. So one thing we have to know is that as the frequency of the muscle potential increases, frequency of contraction also increases. So action potential come close enough together so that the muscle does not have time to completely relax between contractions. So this is when you are vigorously doing an activity. So let's say you are taking a lift and you are doing this. So you are maybe performing an activity. So here you'll be having a multiple wave summation. So usually in tetanus, for instance, muscle spasms, you realize the muscles are just contracting and relaxing uncontrollably. So you don't get the muscles to rest before they contract. So that is what you see in what? Tetanus. And this is also at the supramaximal threshold of the muscle, limit of the muscle. Now, tetanus is actually a disease that is associated with muscle infections. So if you don't take time, it's a toxin directed disease. So we can have incomplete tetanus where muscle fibers partially relax between contraction, and then there is time for calcium to be recycled through the sarcoplasmic reticulum between action potential. But if we have complete, we do not have any relaxation. So this is incomplete, we showed earlier. So at least you can see some relaxations between each of the muscle. And when you come to here, you can see how the curve is now looking like. You don't have that wave formations over here. So you can see that here, you're having complete tetanus, no relaxation. Action potential come totally close, that calcium does not even get any way into the sarcoplasmic reticulum. Then in TREP, we can also see here we are having graded response occurs in muscle resting for prolonged period. You can read, we can all quickly read about this. So this is just to show you that, look, the tension per time within the muscles depend on the size of the muscle and the activity of the muscle. So when you look at here, look at the eye muscle. So the eye muscle has just a shorter time to hold tension. The gastrocnemius, which is around the, gastrocnemius muscle, which is around the posterior aspect of the crus, is also having this time duration for tension, and then the soleus also have this time duration. And you realize that the soleus has a bigger time duration. That means it can hold more tension for a longer time as compared to those ones. So what I'm going to do is that I'll now be moving slowly across the slides, and I want you to take your time and see if you can explain what these curves within these things mean. So we also have a tetanus. This is what is happening. You have to know what is the difference between the internal tension and then the external tension. Why is it that internal tension starts earlier as compared to the external tension and rise a bit. And then there is external tension looks more a bit slopey, but they all fall at the same time. Why does this rise very sharply in the internal tension? And why does this slope? And then why do all they fall very sharply? Those are the questions you need to think about. So this is just to show you sustained submaximal tension or information being delivered from the neural system. So you can see your spinal cord, and then these are the motor nerves which are found at the anterior horn of the spinal cord. And then they go to innervate the myofibers, which make up the myofibril. And then when everything happens, come in, then you have a gross muscle movement. I also want you to look at these graphs very well and tell me why we have the light resistance having a higher curve as compared to the intermediate resistance as compared to the heavy resistance. What characteristics are making this to be like this? So with the question I asked earlier, when you look at this, it should be able to tell you something. For instance, this is a muscle trying to carry 2 kg. The muscle contracts, there's an isotonic contraction, and then you can see how it has shortened for it to lift this 2 kg. So what happens is that the muscle tension, which is in kilograms, you can see that for the muscle length initially, you are seeing contraction going to begin. And then as you want to raise this, the muscle tension increases. So it's the tension that builds in the muscle that will allow you to apply force to overcome the resistance to pick the substance. When you are done, the muscle goes back to its resting potential. Now, so look at 2 kg. Look at what is happening. 0 to 2. And look at the muscle length percentage. Now look at 4 kilograms. It has to take a tension enough to carry this 4 kilograms. So you can see that this is becoming bigger. So if you get this, you'll be able to answer the questions I asked earlier pertaining to the curves. Now let's look at the energy sources that are provided for muscle activation. So ATP provides energy, and then the contraction of the muscle will come. This will come from 3 sources. So the ATP provides immediate energy for muscle contraction from 3 sources. So ATP can come from creatine phosphate. So here during resting condition, store energy to synthesize ATP. So creatine phosphate will store these energies to synthesize ATP when they are needed. Anaerobic respiration occurs in the absence of oxygen and results in the breakdown of glucose to yield ATP and lactic acid. So we can also get ATP from there. Then aerobic we can also get ATP from there. So these are the energy sources. So by now you have done glycolysis and also have done glycogenolysis. So you can see glucose entering the muscle cell, and then there is glycogen formation. Then for glycogen to be formed, there is going to be dephosphorylation of ATP to ADP. For this dephosphorylation of ATP to ADP to occur, then creatinine will be phosphorylated. So the phosphorylation of creatinine will lead to the dephosphorylation of the ATP, and this is going to cause the glucose to be stored as glycogen. For ATP to be provided, this will be produced in the mitochondria where there is phosphorylation of the ADP from those phosphates that has been released as glycolysis and Krebs cycle. And as this thing is being done, carbon dioxide is being respirated. So this is muscle tissue respiration. So look at this graph carefully and see if you can also explain it the way I did. So the question you need to ask yourself is, what is pyruvic acid? What is entering here? Eventually, you'll be able to ask this question, understand. Now, so the question I also ask is, what type of muscle respiration is this? Is it aerobic, anaerobic, or what? The same thing also applies here. Now, let's look at muscle types based on their twitch. So we have a slow twitch or high oxidative muscles. These muscles contract more slowly. They are smaller in diameter, better blood supply. They are very vascularized, and they have more mitochondria. One beautiful thing about this muscle is that they are more fatigue resistant than fast twitch. For the fast twitch or the low oxidative, it means that low supply, they are not that vascularized. They respond quickly to stimulus, and then they have smaller mitochondria than the slow twitch. The distribution of fast twitch and slow twitch, what happens is that most muscles have both, but they vary for each muscle. So if it is a fast working muscle, then you should have a fast twitch. If it's a slow one, you have a slow one. At times, you even have an intermediate. Now, so when you exercise, what happens is that you are going to have hypertrophication of the muscle, where there's increase in muscle mass. However, if you do not, you realize the muscle will go back to its former shape, or it will atrophy. There's muscle loss. So there's some certain diseases like amyotrophic lateral sclerosis and all these things that happen. You are going to have wasting of the muscles. So you can read about all those things. So this is just to show you histologically the difference between slow fiber of slow twitch muscles and the fast twitch muscles. So these are the high oxidative muscles, and these are the low oxidative muscle. Now, fatigue, when we say fatigue, is the decreased capacity to work and reduce efficiency of performance. So when there is fatigue in the body, you realize that efficiency is reduced and your ability to perform work reduces. Fatigue can be psychological. Depends on the emotional state of the individual. Oh, I feel tired. That's fatigue, emotional fatigue. Muscular fatigue results when there is so much, you have worked throughout the day without eating, ATP is depleted. You have muscular fatigue. That it pains your muscle. Synaptic fatigue occurs when the neuromuscular junction due to lack of acetylcholine. So these things, you see them in spasms. There is constant release of acetylcholine. Eventually, you don't have any acetylcholine to release, and then the muscle undergoes fatigue. Now, as you age, one thing is that your muscles will begin to atrophy, and then your stamina will reduce. One thing you have to notice is that the higher the muscle mass, the higher the ability to work, and the more stronger you have, and the more stamina you have. So muscle masses will reduce. That means increased time for muscle to contract in response to nervous stimuli. So you realize that there are certain things you can do so quickly, but when it comes to older people, they take time to do that. That is because of the reduced muscle mass and the reduced stamina. And they also have reduced recovery time. And also at times there is a decrease in the vascularization of this muscle. So this is just to show us the parts of all the muscles as a summary of what we've done today. Muscles are connected to bone, especially skeletal muscles are connected to bone by tendons. It has an organ, muscle organ, which is enclosed in the fascia. The fascia connects a lot of fasciculi, which are also enclosed in the perimysium. Now, the perimysium encloses the myofiber, which is also encloses the myofibril. So after the myofiber, we have the endomyosium. And then when we take the myofibril, we now have our sarcolemma, and then we have our sarcoplasms, and we have our myofibrils, which are made up of the myosin filament and then the actin filament. So thank you very much for today's section of lecture. We'll meet next week to continue. Have a wonderful day.